I mentioned at the outset of this unit that differential equations are considered very, very important, primarily because of their applications. There's lots of fun mathematical theory about differential equations, but most other sciences and disciplines would treat differential equations as one of the most important mathematical tools because they apply to their area of study. Biology, chemistry, physics, economics, they all have differential equation models in them somewhere. And let's see how that appears in context by taking what are fairly straightforward English sentences that describe some scenario and turning them into an equation, and we'll see that those equations tend to be differential equations. All right. The rate at which a potato cools, so this is a heating and cooling physics problem, the rate at which a potato cools off is proportional to the difference between the temperature of the potato and the temperature of the air around the potato. So we have a number of variables here: potato, temperature, so in this scenario we have some potato temperature and air temperature, and the rate at which the potato cools off. Bingo. As soon as we see a rate here, we're talking about a derivative. We're talking about a differential, some derivative of a quantity. So the left-hand side is this derivative, the rate of change of the potato temperature, is proportional to, is a constant times. So the nice thing about these sentences is they really write themselves out on the page. Proportional to the difference. So the difference, of course, is minus sign. One minus the other. Proportional to the difference between the temperature of the potato and the temperature of the air. So this is what we expect drives temperature change when we're talking about an object cooling down. The bigger the temperature difference is, if I put something in a freezer versus something in a fridge, it's going to cool down faster because there's a larger temperature difference. Or we take a very hot potato out of an oven and put it in the air, it's going to cool down more quickly than a lukewarm potato being put in the air. And that's what this expression here is capturing mathematically. There we go. And that's it. That really is a differential equation that comes out of this natural expression of what we expect happens in a particular scenario. And very naturally is a differential equation because we are talking about rates. Let's consider another example. This is one from sociology. The rate at which a rumor spreads is proportional to the product of the people who have heard it and those who have not. Once again, we see that key property, the rate, being included in the equation. So again, we have a rate, which is a derivative, and a rate at which a rumor spreads. We have to be pretty careful about this idea here. What would typically be done in sociology or biology is let P equal the number of people who have heard the rumor. And if we take a look at this, the product of the people who have heard it, so that's our P, and those who have not. So let's call that N, why not? So there's our expression for the number of people who haven't heard the rumor. What we're talking about when we talk about the rate at which a rumor spreads, well, you're talking about a derivative, but the derivative of what? What you're talking about is increasing P. As a rumor spreads, more people have heard it. So our differential equation is going to be defined by the rate of change of the number of people who have heard the rumor, or the derivative of P. Once again, we have our is proportional to is equal to a constant times. And what else do we have? It's equal simply to the product of the number of people who have heard the rumor and the number of people who have not. And if you're interested, the motivation behind this is, if there's only a few people who haven't heard the rumor, then what happens? Well, most people who have heard the rumor are talking to each other and sharing the gossip, and nothing's new there. So the fewer people that there are who are still uneducated in this matter, the lower the rate is going to be, the rate of spreading. And that's pretty much it. At least for a first naive implementation or formalization of this differential equation. It is worth noting, though, that we can make this equation a little simpler in the sense that here we have two variables that are very closely related to each other. One is the people who have heard the rumor, one is the people who have not. And there's a natural trade-off between those two. And let's let C be the total population. If we have a total population of C, then the number of people who have heard and have not heard, when we add them together, that adds up to C, because it's either you have or haven't heard it, and everybody in the population can be divided into one of those two categories. And what we can then do is isolate either one. I would say let's isolate the one we want to get rid of, the people who have not heard the rumor. And then we can re-express our differential equation as a constant times P, then times our population minus P. And this has the advantage of it's all in terms of P and constants of various types, rate constants and population constants. So this is a classic differential equation in population biology and sociology, and we're going to actually explore this more thoroughly as we go through this unit. For now, we'll settle for having written it out based on some premise of some argument about how rumors spread and how it shows how we're able to use that to create a differential equation model that captures exactly that idea of how a rumor spreads. All right, let's look at a little more physical example here. The rate at which water is leaking from a tank. So I've got some tank, there we go, and there's some hole in the bottom, or if you're talking a water barrel, that kind of thing. You can make an energy argument that shows that the rate at which the water leaves the tank under the force of gravity is proportional to the square root of the volume. All right. So here, oops, we would let V equal our volume of water. Whoops. In the tank. And as soon as we say the rate at which water is leaking, well, that's causing a decrease in the volume in the tank. We're losing water. So the rate at which water is leaving the tank is proportional to, there we go, constant times, the square root of the volume of water in the tank. And the one thing I would start adding now is explicit sign notation. The reason it makes sense to put a negative sign here is because V, being the volume of water in the tank, if that's a rate of change of the volume with a leak, it'll have to be negative. That way we can keep our constant positive. This is a positive square root. And so this explicitly tells us at a glance that we've got the volume decreasing. That dV dt is negative. So the volume in the tank is decreasing. So that's an important thing to be able to look at a differential equation and understand the various terms in it. So the rate of change of volume in this tank is proportional to our constant times. We don't need this minus because we could have a negative constant, but in most equations you'll see written down, if there is an important sign, it'll be written out explicitly like this, just to make it clear, are things going up or going down at a glance. Last but not least, let's return to something similar to the integral examples we saw earlier in the course, where we were using the universal law of gravitation. You've got a meteorite plummeting towards the Earth. Its acceleration is inversely proportional to the square of its distance from the center of the Earth. All right. So let d equal distance between meteorite and the center of the Earth. And if that's the case, its acceleration will be the second, let's actually use that as a capital D so we don't get confused with our derivative d's. So its acceleration is going to be the second derivative of that distance. And if that's the case, then our differential equation says its acceleration, there we are, is inversely proportional, k over the square of its distance from the center of the Earth. So the acceleration is proportional to k over the distance squared. And again, we could do some analysis of signs here and ask, well, is the acceleration positive or negative? And we'll leave that for now, though, because that would take a little more study than this example really needs. All of these are showing us that by understanding or making some statement about a system, we can fairly quickly get to a differential equation model for it. Now, again, this is the first time we've seen differential equation models. What we're missing as a second stage here is getting to what the prediction is as the result of that differential equation. We start with this based on our understanding of the system. But what do we do with this equation once we have it? We've only seen very simple examples of solutions, so we're going to have to explore this much more thoroughly as we go forward.